Good day everyone, I am Thérèse from the University of the West Indies, and today I'll be presenting on developing network models of industrial symbiosis. In this presentation, I'll go through some background of industrial symbiosis, the network models we developed, our findings, and our conclusions. So what is industrial symbiosis or IS? IS is the physical material exchange among companies. Materials could include water, energy, waste, or byproducts. Ideally, companies should be near to each other so that the transportation cost of the material would be low. IS is a great waste management solution since it reduces the amount of waste emitted to the environment and also reduces the amount of virgin raw materials needed in a process. In the diagram here, there's an eco-industrial park or an EIP in which IS exchanges are occurring. For example, from the power station, waste heat is sent to many different processes. There's no standard means of measuring IS. There's mass flow analysis and life cycle analysis, but by themselves they aren't sufficient to measure IS. Therefore, there's a need for indicators. Connectance and symbiotic utilization is similar to what you see in a food chain or a food web. So IS is determined by the number of links. Waste recycling rate has to do with the amount of waste being recycled, and environmental impact momentum has to do with the amount by which IS changes in a network. In this study, the material being exchanged is carbon dioxide or CO2. The reason for selecting CO2 is that it is a greenhouse gas, and in Trinidad and Tobago, there's a high CO2 emission per capita, and this comes mainly from the petrochemical industry, which is located in the Point Lisas industrial estate. Additionally, CO2 could be very helpful in creation of valuable products. The CO2 we're going to look at in this study is from the rich CO2 streams. So in the estate, there are rich CO2 streams and lean CO2 streams. Examples of rich CO2 streams would be from the ammonia process, for example, and lean CO2 streams would be from flue gases. The study will focus on the Point Lisas industrial estate. Initially, we developed a simple transportation model looking at ammonia and methanol plants. So our sources are ammonia plants, which emit CO2 from their process, and the sinks are methanol plants, which require CO2 for their process. So here we have A1 and A2, which are ammonia plants, and M1 to M4, which are methanol plants, and W is the waste. So here we show the possible CO2 network linkages for this model. Based on the plant capacities of these plants, we developed the model, and here we show the possible flows of CO2 from the sources to the sinks. As you can see, there is some waste CO2 being generated to the environment. We expanded the model to be approximately half of the Point Lisas industrial estate. And when I say this, I mean that we looked at the plants requiring or releasing high purity CO2. So our sources here are ammonia plants, A1 to A5, our sinks, M1 to M3, which are methanol plants, U is a urea plant, and W is waste, which is CO2 which is generated to the environment. So here we see the possible links. Also note that urea gets all its CO2 from A1. After establishing the possible links between the sources and the sinks, it is necessary to determine the actual flow rate requirement by the sinks and that being produced from the sources. So we conducted an enterprise input-output analysis and developed an input-output table or an EIO table. And this looks at the output and input to the process. So here we see for the ammonia plant, the main product is ammonia being produced at 78 tons per hour. And the CO2 is the byproduct, which is the rich CO2 being produced at 95 tons per hour. A similar analysis was done for methanol, and as we can see, for every 59 tons per hour methanol being produced, 18 tons per hour of high purity CO2 is required. After developing the EIO table, we assessed IS based on the indicators which were previously mentioned. So the base case here is a case where there is no industrial symbiosis occurring in the network. That means there are no links among the companies and all waste generated to the environment. The current case here is with our linkages. So as we can see, compared to our base case, any positive value or greater than 0 indicates that there is some level of IS occurring. In a previous slide, we saw the possible linkages between the sources and the sinks. So this showed all the possible routes for sending CO2 from the sources to the sinks. But how do we know which route we should use, or what is our best option? This is where optimization comes in. In this study, we looked at both single and multi-objective optimization, looking at the objective to minimize waste CO2 to the environment, as well as cost. And the cost to refer to here is the levelized transportation cost of CO2 from the source to the sink. In this presentation, I'll be focusing on the results from the multi-objective optimization, or MOO, where the objective function was to minimize waste CO2 and cost. The constraints used in this model were based on the supply and demand, or the sink and source requirements. Binary variables were used for restricting small flows in the pipelines in the network, and hence this made the problem a mixed integer linear programming, or MILP problem. The MOO MILP CO2 network was developed in MATLAB using the genetic algorithm multi-objective function. This gave the Pareto front, which contained multiple solutions, and we selected the best solution in terms of cost and the flows. We can see here that a large amount of unused CO2 is still present, and the CO2 transportation was around US $11.4 million. We consider the case of adding a CO2 reuse plant to the network as well. The CO2 reuse plant we added was propylene carbonate, or as we can see here, P. So this propylene carbonate plant was first modeled using Aspen Plus, and it was also costed. And the information we obtained was added to the EIO and the optimization model. Multi-objective optimization was also done for this proposed case, and we can see that it led to a reduction in waste CO2 as expected. The CO2 transportation cost increased to $13.6 million as expected, since we have introduced a new CO2 plant and therefore more pipelines are required. We redid the IS assessment using the same IS indicators that we did for the current and the base case. And as we can see here from our results, all our indicators increased, indicating that there was a higher level of IS when this propylene carbonate plant was added to the network. Finally, we consider the 3 pillars of sustainability for the current and proposed case. As we can see here, all 3 dimensions will increase for the proposed case except the eco-efficiency. Now, the eco-efficiency we use here was more of a resource efficiency, which is based on the amount of product being produced. So this is something we need to keep in mind when we are adding a CO2 reuse plant to our network. From this study, we can conclude that EIO models with process simulation data can be used to analyze or optimize IS scenarios. PLIE's industrial estate already has some characteristics of an EIP and also has some level of IS occurring. There's a large amount of CO2, which is high purity, that is available for reuse, and reusing this CO2 should lead to higher amounts of IS and triple bottom line benefits in the network. The following is a list of some of the references used in this presentation. I'd like to thank you for your time and attention. If you have any questions, you can direct these to Dr. James or myself via email. Thank you.